Golden Iris Productions presents Chapter 1, From Newton to Einstein, The Story of Gravity. The Greeks. The story begins with the ancient Greeks, who showed an extraordinary ability to use simple observations to uncover deep truths about the world. Eratosthenes, working in the 3rd century BCE, noticed that at noon on the summer solstice, the sun cast no shadow in Cyane, but did cast a measurable shadow in Alexandria. By comparing the angle of that shadow with the known distance between the two cities, he used basic geometry to estimate Earth's circumference with surprising accuracy. This achievement demonstrated how curiosity and mathematical reasoning could reveal the scale of the planet long before modern instruments existed. Copernicus. More than a millennium later, Nicolaus Copernicus revived that spirit of inquiry by proposing a radical reordering of the universe. In De Revolutionibus, he argued that the sun, not the Earth, sat at the center of planetary motion. Although he presented his model cautiously as a mathematical convenience, the implications were profound. His heliocentric system challenged long-standing assumptions inherited from Aristotle and Ptolemy, and quietly shifted humanity's sense of its place in the cosmos. The Church. The Church's reaction to heliocentrism developed slowly, shaped by tradition, theology, and institutional caution. For centuries, scriptural interpretation had been aligned with a geocentric worldview, making Copernicus's ideas unsettling. As observational evidence accumulated, especially through Galileo's telescopic discoveries, the tension grew. Galileo's 1633 trial became a symbol of the struggle between emerging scientific methods and established doctrinal authority. Kepler. Johannes Kepler transformed Copernicus's conceptual breakthrough into a precise, predictive science. Using Tycho Brahe's meticulous observations, he discovered that planets move in ellipses rather than perfect circles. His 3 laws of planetary motion described how planets sweep out equal areas in equal times, and how their orbital periods relate to their distances from the Sun. These laws revealed a deep, elegant order in celestial motion. Kepler saw this harmony as almost musical, a cosmic architecture governed by mathematical principles. His work provided the structure Newton would later unify under a single physical framework. Galileo. Galileo revolutionized the study of motion by showing that falling objects do not move at a constant speed, but accelerate as they fall. Through inclined plane experiments, he demonstrated that the acceleration is the same for all bodies regardless of their mass. He measured this constant acceleration to be about g is approximately 9.8 meters per second squared. This insight laid the foundation for Newton's later work by revealing that gravity acts as a uniform, measurable acceleration. Chapter 2. Newton unifies the universe. Isaac Newton brought the entire narrative together by showing that the same physical laws apply both on Earth and in the heavens. In the Principia, he introduced the 3 laws of motion and the law of universal gravitation. Newton demonstrated that the force pulling an apple downward is the same force that keeps the moon in orbit. This insight explained Kepler's laws and validated the heliocentric model. His synthesis didn't just solve astronomical puzzles, it redefined scientific explanation itself. Newton showed that the universe could be understood through universal principles expressed in precise mathematical language, completing the arc that began with the Greeks. Newton's gravitational equation. Newton began by relating the masses of 2 objects and the distance between them. His early expression looked like m1 times m2 divided by r. This captured the idea that gravity grows with mass and weakens with distance. The raw numbers were enormous. To express gravity as a measurable force in meters, kilograms, and seconds, Newton introduced a scaling factor, the gravitational constant, g. To turn his gravitational idea into a real force, Newton introduced the constant g. This constant scales the mass-distance ratio into a physical force.
Newton's universal law of gravity. Newton's final equation is F equals g times m1 times m2 divided by r squared. This unified falling objects on Earth with the motion of planets. Newton's second law says F equals ma. For falling objects, this becomes F equals mg. Set the two expressions equal. mg equals g times capital M times m divided by r squared. Cancel m, giving g equals g times capital M divided by r squared.
Chapter 3. Orbital Mechanics. The Moon. The Moon is constantly falling towards Earth, but its sideways speed is high enough that it keeps missing the Earth. This balance creates a stable orbit. Centripetal acceleration is a sub c equals v squared over r. Gravity provides this acceleration. V squared over r equals gm over r squared. Solving for orbital velocity gives v equals the square root of gm over r. Orbital velocity. Escape velocity is different from orbital velocity. To escape, an object must have enough kinetic energy to climb completely out of Earth's gravitational well. We express this by setting kinetic energy equal to the magnitude of gravitational potential energy. 1/2 mv squared equals gmm over r. Solving for v gives the escape velocity. Cancel m and rearrange to get v sub escape equals the square root of 2gm over r. This is why escape velocity is the square root of 2 times the circular orbital velocity. Using r equals 3.844 times 10 to the 8th meters, we obtain v is approximately 1.0 kilometers per second, matching the Moon's observed orbital speed. The orbital velocity formula, v equals the square root of gm over r, applies to any orbiting object. Replace Earth's mass with the Sun's mass to get v equals the square root of g times m sub sun over r. This gives planetary orbital speeds such as Earth's 29.8 kilometers per second. The orbital period is t equals 2 pi r divided by v. Substituting v gives t squared equals 4 pi squared over gm times r cubed. Newton showed that all orbiting bodies obey t squared is proportional to r cubed. This unified planetary motion with physics on Earth. Chapter 4. Mercury's Orbit and General Relativity. Mercury. Mercury's orbit precesses slightly over time. Newton's laws explained most of it, but an extra 43 arcseconds per century remained unexplained. Einstein's general relativity describes gravity as curved spacetime. Near the Sun, spacetime curvature alters Mercury's orbit. Einstein's prediction matched the unexplained 43 arcseconds per century. General relativity. Einstein expressed gravity as g mu nu equals 8 pi g over c squared times t mu nu. The left side represents curvature of spacetime. The right side represents energy and momentum of matter. Newton's universal law of gravitation says F equals g times m1 times m2 divided by r squared. Einstein's field equation says g mu nu equals 8 pi g over c squared times t mu nu. Both contain the same gravitational constant, g. By 1915,
Einstein had completed special relativity and was developing general relativity, a theory in which gravity is the curvature of spacetime. He believed his field equations were so complex that only approximate solutions would ever be possible. While serving on the Eastern Front in World War I, Karl Schwarzschild read Einstein's newly published field equations. Despite wartime conditions, he discovered the first exact solution for the spacetime around a spherical mass. He sent this solution to Einstein, who was astonished by its simplicity. Schwarzschild's solution revealed a special radius, r sub s equals 2gm over c squared. This radius marks a boundary where spacetime curvature becomes so extreme that not even light can escape, the first mathematical description of a black hole. Escape velocity is v sub escape equals the square root of 2gm over r. Set this equal to the speed of light. C equals the square root of 2gm over r. Solving for r gives r equals 2gm over c squared. This is exactly the Schwarzschild radius. At any radius smaller than r sub s, all possible paths curve inward. Even light cannot escape. This boundary is called the event horizon. To compare escape velocity with the speed of light, v sub escape over c equals the square root of 2gm over rc squared. When this fraction approaches 1, gravity becomes extremely strong. Set escape velocity equals 0.98 c. 0.98 equals the square root of 2gm over rc squared. Squaring gives 0.9604 equals 2gm over rc squared. Solving for r gives r equals 2gm divided by 0.9604 times c squared. This radius is only about 4.1% larger than the Schwarzschild radius. To be escape velocity equal to the speed of light gives c equals the square root of 2gm over r, which leads to r equals 2gm over c squared. This is exactly the Schwarzschild radius. At r equals rs, spacetime curves so strongly that all possible paths curve inward. Even light cannot escape. This boundary is called the event horizon. Inside it, escape is impossible, the defining feature of a black hole. The story of gravity begins with Isaac Newton, who unified falling objects and planetary motion with his law of universal gravitation. His equations explained the structure of the solar system, yet Mercury's orbit contained a small but persistent anomaly that Newtonian physics could not resolve. Albert Einstein resolved Mercury's anomaly with general relativity, a theory in which gravity is the curvature of spacetime rather than a force. His field equation linked matter and energy to geometry and correctly predicted Mercury's unexplained precession. Soon after Einstein published his theory, Karl Schwarzschild found the first exact solution to the field equation. His work revealed a critical radius, r sub s equals 2gm over c squared, where spacetime becomes so curved that even light cannot escape. The Schwarzschild radius defines the event horizon, a boundary beyond which escape is impossible. What began with Newton's study of motion ultimately led to Einstein's curved spacetime and Schwarzschild's prediction of regions where the universe itself traps light. We have traced gravity from Newton's force law to Einstein's curved spacetime to Schwarzschild's prediction of black holes. These ideas describe the universe on the largest scales. To understand the universe on these smallest scales, we now shift to the quantum world, where electric charge replaces mass as the fundamental source of interaction. This transition leads us from gravitational curvature to the structure of electric and magnetic fields, and ultimately to the foundations of quantum physics. To be continued.
To be continued.